Today, we are diving into the infamous copy fail bug, a Linux privilege escalation bug. First, let me give you a quick sentence of how this bug works, which you can relay to a CISO or SLT manager who has somehow managed to fail upward into the role. Linux exposes a crypto API which trusts attacker-controlled input and then lets that input influence where and what the kernel writes. This allows the user to change files it should never have write access to. For example, an attacker can abuse this to overwrite etc password-related memory and elevate privileges from a normal user to root. For this video, I've created a modified version of rootsekdev's exploit, which walks you through the vulnerabilities, whilst showing you bits of the Linux memory we are changing. The first thing the exploit does is find the exact byte position of the current user's UID inside the etc password file. On my machine, that's byte 1386, where the UID 1000 for my user RTR lives. Next, the exploit does an open read on the etc password file. This ensures it has been loaded into page cache. It's important to understand what page cache is, so here's a quick explanation. The page cache is basically Linux holding file data in memory, so it does not have to keep going back to disk every time the file is read. Only the kernel is supposed to manage and modify the page cache. As a normal user, we should have absolutely no business changing those bytes directly. However, copy-fail chains three issues together, letting us influence the kernel into changing them for us. First, AFALG gives userland a legitimate way to send data into the kernel crypto system through a socket. That part is by design. We want user space programs to be able to ask the kernel to encrypt and decrypt data, rather than every application having to implement its own crypto from scratch. In the exploit, we first open the socket and then bind it to the auth-enc ESN algorithm using HMAC SHA-256. And then using send message, we provide the data we want the kernel crypto code to process. So send message contains AAD, CMessage, socket.messageMore. AAD consists of 8 bytes containing 2 parts. The first 4 bytes are filler, and the next 4 bytes are the value we actually want written. In our case, those important 4 bytes are 30, 30, 30, 30, which is the ASCII representation of 0000. The CMessage flags were set at the top of the code. Importantly, we set a sock-len to 8, which matches the size of our AAD. This is important and I will explain later. Message more tells the socket to stay open because we will be sending more data. Here comes our second issue. AFALG was extended to support splice, and this is where things start getting interesting. Instead of copying normal userland data into the crypto socket, Splice can pass the kernel a reference to file-backed memory. More specifically, it can point to data sitting in the page cache, which we talked about earlier. AFALG takes the data we just provided and represents it as a scatter gather list because it is preparing that data to be passed into the kernel crypto system for decryption. A scattered gather list is basically a list of memory chunks. Instead of copying everything into one clean buffer, AFALG can describe where the different pieces of data already live in memory and then hand the layout to the decryption code. However, because we used Splice, we managed to place a reference to the page-cached etc password file inside that list. Now we get to the third issue, the scratch write. The vulnerable crypto code uses something called auth-enc ESN. During decryption, it performs a small 4-byte scratch write at a calculated position inside the scatter-gather list. So the important question is, how do we make that position land exactly where we want? The crypto function needs to perform its 4-byte write from AAD into the scatter list below at the location asoclen plus cryptlen. Asoclen is our AAD, so it equals 8 bytes. Cryptlen is the total length of the data we sent in minus the asoclen minus auth tag size. Auth tag size is 32 bytes, as that is what we spliced in earlier. So cryptlen becomes 40 minus 8 minus 32, which equals 0. That means the scratch write offset becomes asoclen plus cryptlen. 8 plus 0 equals 8. And offset 8 is important because our AAD is exactly 8 bytes long. So logical offset 8 is the first byte immediately after the AAD. And what did we put immediately after the AAD? The spliced page cache reference to etc password. So when authink ESN performs its 4-byte scratch write, it lands at the start of the spliced page cache segment. The kernel thinks it is doing a tiny internal scratch write during decryption. But because we controlled the layout, that 4-byte write lands inside the cached etc password data. And because the 4 bytes we prepared earlier are 30, 30, 30, 30, the kernel ends up writing the ASCII string 0000 over our UID, which gives us root access to the operating system. So, we've patched a page cache memory of etc password to tell the OS we are root. Until the system restarts or page cache does a refresh from disk, we will have root privileges. Here is a full animation from start to finish of the exploit. Go and check out that code on my GitHub if you want to get a feel for it yourself. It's the best way to learn.